That's exactly why some physicists started thinking outside the box. Not about accelerating the ship, but about manipulating the space around it instead. In 1994, Mexican physicist Miguel Alcubierre proposed a fascinating mathematical idea within the framework of general relativity. His idea wasn't to accelerate the ship, it was to create a bubble of space-time around the ship, contracting space in front of it, and expanding space behind it. This way, the ship itself never moves faster than light within its own local bubble, which keeps relativity intact. But the bubble as a whole could travel through space faster than light, because it's space itself doing the moving, not the ship. And there's no known upper limit on how fast space itself can expand. This actually already happens in our universe. The expansion of the cosmos itself causes distant galaxies to recede from us faster than the speed of light. A genuinely brilliant idea, mathematically. But the trouble starts the moment you try to move from the equation to reality. To bend space-time into this bubble shape, Alcubierre's equations require what's called negative energy density, something that has never been observed in nature in any significant amount. The closest thing we have is the Casimir effect, a tiny quantum phenomenon that produces minuscule amounts of negative energy, nowhere close to what would be needed to move a bubble the size of a spacecraft. Then there's the energy problem itself. Alcubierre's original calculations suggested the energy required would exceed the mass energy of the entire observable universe. Later research, notably from physicist Harold White at NASA, attempted to shrink that number significantly by reshaping the bubble's geometry. But even in the most optimistic estimates, the energy required still vastly exceeds anything a human civilization could realistically produce in any foreseeable future. Even if the energy existed, later studies suggest a warp bubble could be quantum mechanically unstable, potentially collapsing or breaking apart the moment you try to move it at superluminal speed. High-energy particles and radiation could also accumulate at the front of the bubble, making it dangerous to anything inside it, or anything it eventually releases upon stopping. And then there's the deepest problem of all, causality. One of the most debated issues in theoretical physics is that any faster-than-light travel could, in principle, open the door to time travel, or to what's called closed time-like curves, something that directly conflicts with the principle of causality our entire understanding of the universe is built on. But here's the most important part of this video. Let's say, hypothetically, humanity overcame every single one of these obstacles, enough energy, stable exotic matter, and a solution to the causality problem. Would that mean the entire universe is finally within reach? The answer is still no, because of one massive factor: the expansion of the universe. The universe isn't just expanding, its expansion is accelerating. That means there are galaxies and objects so distant that they are already receding from us faster than the speed of light today, purely because of the expansion of space itself, not because of any motion of their own. These objects sit beyond what's called the cosmic horizon, permanently unreachable, not because of a lack of technology, but because the space between us and them is stretching faster than any signal or ship could ever cross it. In other words, even with a flawless, perfectly functioning warp drive with no limitations at all, a huge portion of the universe would remain forever out of reach, as if the universe itself was built to place a hard limit on any civilization, no matter how advanced. What we've learned today isn't just a fact about a fictional engine. It's a deeper lesson about the nature of the universe we live in. A universe so vast that even the smartest physics humanity has ever devised might not be enough to close the real distance between stars and galaxies. That doesn't mean the dream is completely impossible. Future physics might reveal phenomena we haven't discovered yet. But it does mean that if humanity's journey to the stars ever happens, it will likely be far slower and far harder than science fiction has led us to imagine. If you enjoyed this journey into real physics, and you want more content that combines scientific accuracy with genuine wonder, don't forget to subscribe and turn on notifications so you never miss a new video. Let us know in the comments, do you think humanity will ever reach another star? See you in the next video. Imagine we had it right now. A real, working warp drive. A ship capable of bending space-time itself, breaking past the speed of light. The same technology we've watched in science fiction for decades. Would that finally be enough to reach the nearest star? The answer is no. And by the end of this video, you're going to understand why, in a way that will completely change how you think about the size of the universe, and why even the most powerful technology we can imagine might not be enough to close the gap between us and the stars. In this video, we're going deep, the real scale of interstellar distances, how a warp drive would actually work according to real physics, and why, even if we solved every single engineering problem standing in its way, the universe itself might still keep the stars out of reach. Before we get into it, if you're into science content built on real physics instead of just imagination, hit subscribe and turn on notifications, because what you're about to hear might change the way you think about humanity's dream of reaching another star. Let's start with the actual scale of the problem we're trying to solve. The closest star to the Sun is Proxima Centauri, sitting about 4.24 light-years away. That number sounds small when you say it out loud, but a single light-year is the distance light travels in one full year, moving at nearly 300,000 kilometers per second. Here's what that actually means. If we launch today using the fastest spacecraft humanity has ever built, the Parker Solar Probe, which reaches speeds of roughly 690,000 kilometers per hour, it would take about 6,800 years just to reach the nearest star. 68 centuries for the closest star. Not another solar system, not another galaxy, just our nearest neighbor, and that's the closest star. Our galactic center is about 26,000 light-years away. The Andromeda Galaxy, our nearest large galactic neighbor, is over 2 million light-years away. This is the real problem. It's not a limitation of rocket engines. It's a limitation baked into the structure of the universe itself. So the obvious answer seems simple. Just build a more powerful engine. But this is where Einstein's special relativity comes in. As any object with mass approaches the speed of light, the energy required to accelerate it further increases dramatically, and not in a straight line. To actually reach the speed of light, you would need infinite energy, which is simply impossible for anything that has mass. In other words, no matter how advanced propulsion technology becomes, the speed of light stays an unbreakable wall for conventional travel, pushing a massive object harder and harder.